This meeting is being
Go
recorded.
ahead, Ravi.
Thank you, Mr. Ken. Professor Ken Beklowski. He is our Ontolog Forum Chair. And this year I am Ravi Sharma, the Chair of Ontology Summit 2022. I am very, very delighted to welcome our speakers of today. And we are starting a new track today. It is called Track 4, Space, Aerospace Disasters, including debris and other aspects. So my co-champion is Robert Ruvito. He is well known to our speakers today. Our speaker is also joined by Yvonne, his colleague, and Robert will tell us more about it. I just want to conclude my opening statement by saying that I have about 10 years of direct, contract, or various projects experience in NASA. The first one started in 1968 with Apollo program, continued to 72, and the second inning started in 96 and continued to 2000. Thereafter also, I have been working on JPDO's next generation airspace management, which included, of course, intermediary to satellites and low Earth satellites as well. So with my own Apollo Achievement Award is the only distinction I have in life. And with that, I just conclude that I am very great enthusiastic person for space program. And I welcome all my colleagues who are joining, and I hand it over now to Robert Roberto.
Thank you, Ravi. And to be fair to Ravi, he kicked off track 4 a couple of sessions ago. I'd recommend his talk as part of 2 sessions ago, part of that session. So if anyone is interested, please look at the Summit, the Ontology Summit website for his talk. Today, we have Scott Hull, and he serves as the lead orbital debris engineer for Goddard Space Flight Center, NASA. He has over 20 years experience performing orbital debris assessments, consulting on decommissioning planning, and providing related studies over 60 missions. Mr. Hull also has supported 6 orbital debris related studies for the NASA Engineering and Safety Center, and authored or co-authored, over a dozen conference papers and chapters for 2 textbooks. He graduated from Drexel University with a degree in materials engineering. And we also have Yvonne Rodriguez, excuse me for the pronunciation, and she is also with NASA. She's an orbital debris specialist. And on a personal note, I'm happy that both are attending today. We, the 3 of us, met in 2016, I believe, at the Center for Orbital Debris Education and Research out of the University of Maryland. And Scott has been kind to serve as a subject matter expert where I consulted him for some of my ontology modeling work. So with that, I'm pleased that they're both in attendance and can speak today. And Scott, take it off. Thank you.
Okay, thanks, Robert. Let's see. If the technology is working, you should see my slides.
Looks good.
Okay, thanks. So, like Robert said, I've been working orbital debris for over 20 years. Yvonne came on to help me, just for 1 year, and that was 16 years ago. So that's it's worked out really well, and I'm glad that she's here to join me today. If I don't have the answers to questions, I'm sure she will. I'm going to do my best to stay on track and allow 15-20 minutes for questions at the end. I really like to talk, so once you get me going, I need to watch the clock. So, talking about potential space debris disasters. We don't really like the word disaster To us, uh, any failure can be a disaster depending on whose perspective. Uh, obviously, if it's something that leads to a a risk or a close call or an injury to the crew, yeah, that's going to make the news everywhere. Everybody's going to hear about it. If nothing else, it's a public relations disaster globally for the agency. Yeah, we understand that. But let's say Goddard builds a satellite. We design it, we build it, we test it, everything's great. We put it on the launch vehicle and the rocket explodes. Well, okay, that's probably not going to make the evening news. Most of the public might not hear about it at all. But to the principal scientist who was relying on that data for his, maybe the rest of his career, that's a disaster to him. It's a disaster to everyone who did that design and construction and testing. So what we talk about instead is in terms of risks. And there's a whole division within NASA that uh, assesses and manages risk. So we have some challenges that are unique, some that aren't unique, but are still very meaningful for space. The biggest, of course, is the remote location. Something fails up there, repairs are very, very difficult. Hubble was was uh, a, a was an exception, excuse me, exception to that rule. They, even then, those repairs were not at all easy. It took years to plan every one of those servicing missions. It's difficult or impossible to rescue the crew. So operating remotely is a huge challenge for us. Um, we face human error just like everybody else does. And if somebody sends the wrong command, there can be consequences. And so we have to protect against that as much as we can. Of course, we're seeing a radiation environment in space that you don't see on the Earth. And I'll talk some about the total dose and single event effects. Orbital debris, of course, is where I make my money. We're looking at the orbital debris and meteoroid risks to manned missions as well as the robotic. And I will talk mostly about things that we see in Earth orbit because that's where most of our missions are. But most of these apply, some even more so, beyond Earth orbit. Okay, so I already used the wrong word once. We try not to say manned missions. We talk crude missions now. That's crew with a W, not crude with a D, with the CRUDE. Crude missions. You've got people on board. They're obviously very high visibility, many billions of dollars. Um, we're talking lives. And like I said, if something happens that even endangers the crew, you're going to hear about it on the evening news. Extremely high visibility. So it carries a much lower acceptable risk. That only stands to reason. We check things more often. We do more testing. We build in more redundancy on those missions. Robotic missions are the ones that don't have a crew on board. So they're lower visibility, but these things can still run up into multiple billions of dollars. The science data is the big thing that's at risk, as opposed to risking people. So that risk threshold can vary based on what the mission does. For James Webb Space Telescope that recently launched, had a fairly low tolerance for risk, despite the fact that it was a very aggressive mission, and we're amazed that it's going as well as it is. The operations are very carefully conducted, but maybe we don't have quite as many checks as you might have on something like the station. And we can allow some single point failures, but we build in safeguards to make sure that those won't come to happen. Okay, so I mentioned before, operating remotely brings its own set of risks. Even if the crew were somehow endangered this afternoon, it would take at least 1 week, 2 weeks, maybe longer before we would be able to launch any sort of a rescue mission or even repair or resupply that's not already on the schedule. It's not like we keep rockets sitting around waiting to go and you can just, toss some stuff in and punch the button. That works great in the movies, but it doesn't happen in real life. So that's a big risk. The space station is visited frequently, so we've got scheduled revisits, we've got scheduled resupply missions, but most of those resupply missions can't handle crew. So we could send up some repair supplies, we could send up more food, whatever, but we can't bring people down with those missions. Robotic missions generally have a safe hold built into them. So if things start going wrong, let's say the spacecraft hasn't heard from anybody on the ground for 24 hours. That alone might be enough to put it into safe hold mode, because it simply says, hey, something's going wrong here. Maybe the the receiver's not working. What's going on? And so it will go into a safe mode to protect everything else on the spacecraft. We see that, work through the problem, send any commands that are necessary, and hopefully recover from safe hold. So that's how robotic missions work around this idea that everything is remote and hard to access. Okay, so in space we see a lot of radiation that on the ground is mostly filtered out by the magnetic fields around the Earth. We look at two basic things. I used to be a parts engineer, and I think my next slide talks to something that happened while I was a parts engineer. And we look at two different types of radiation. One is simply the total dose of background radiation. So simple, the longer you stay there, the more radiation you collect, and the parts wear out. It's just like a wear out mechanism on your car or anything else. The longer you use it, the more likely it is to fail. We do a lot of accelerated ground testing, where we'll park a circuit, more often microcircuits, but could be diodes or transistors or just about any active part. Park that in front of a source for a week, 2 weeks, 3 weeks, whatever the test calls for, and then test them afterward to see how well they still work. One of the things that happens is that there's an annealing effect, where if you bombard the part with very high doses, it's going to cause more damage than if you were to put it in space and let it accumulate that amount of radiation over the course of years. So fortunately, that our testing is a worst case. It's a little harsher environment than we actually see in orbit. the only mission that I was ever assigned to only one mission at a time was Hubble. And so I was the electronic parts engineer on Hubble for over 3 years. And at that point, the telescope had already been on orbit for 10 years. It's designed for, I think, 15. So I was already a little itchy then about the total dose. And now she's been up for more than 30 years. So, and those parts are still working. The other thing we look at is single event effects. That's where one really highly charged particle comes through. And if you're lucky, it just causes a little upset. Maybe hits a memory circuit and a 1 turns into a 0 and you get a data point that just doesn't make any sense. Or other small effects can happen, and we have ways to filter those out. If you're unlucky, the particle comes through, hits one of the power transistors and causes it to flip, and now that's the same as if you sent an errant command. So we have to protect against those as well, because that can actually cause enough current to burn out a circuit if you don't catch it in time. So the way we catch those things, we build in what's called error detection and correction. So we have ways of looking at that memory bank and telling whether it produced any errors. And if they do, we tell the ground, hey, look, there's an error in here somewhere. I think it's in this spot. And the ground can look through and say, okay, yeah, this point doesn't make any sense, and they fix it. More importantly, those error detection can pick up a latch up and shut things down real quickly to protect the rest of the equipment. Yep. So here's an example of what happened. I believe this was Christmas Day 1999 or something like that. It was right before 2000. So we launched the Terra Earth observing satellite, and I get a call at home okay, we need you to come in here and try to help us understand what's going on with this thing. Every time it comes around over the South Atlantic Ocean, the thing turns off all the instruments. Well, that's very unfortunate, because it comes over that spot 3 or 4 times per day, and you don't want that happening to your data stream, that everything shuts down and has to restart. So we go in and we look at the parts list, and it became immediately obvious to the radiation guy and to me what part was causing the problem, because I don't want to say, misquote the part number, but it was an optocoupler. And the way those work, it's got an LED and a phototransistor. And when you want an electrical isolation between 2 circuits, but you still want this signal to get to this circuit, you can have that LED lights up. The transistor says, oh, I got a signal. Okay, works great. You can use them all. We use them all over the place. But what was happening is that in the South Atlantic anomaly, there's a point, the South Atlantic, there's a spot where high energy single event effect radiation penetrates through the magnetic fields and can cause things to happen. And in this case, there's a little bit of silicone as a light pipe between that LED and transistor. And that silicone would light up when single event radiation hit it. Transistor says, oh, I got a signal, and shuts off all the instruments. So that was unfortunate. And you say, okay, well, why didn't you know about that? It turns out that we did that test, I think 3 days before the launch. So we learned this thing. Great. So it was fresh in our minds when we picked up that parts list and said, oh, that's the one that's causing it. So we do the best we can, but the calendar still gets in the way sometimes. You know, if we do the test on Wednesday and launch on Saturday, there's no way we're going to redesign and rebuild the hardware. Fortunately, we were able to upload a new software edit that says, no, if you receive one pulse, that's, you know, look for at least a second pulse over this short period of time. And if you don't get a second pulse, then don't reset. Still enough to protect the instruments, but now it's not sensitive to that one pulse that comes through. So that's a case where being flexible, the ability to upload new software saved the whole mission. Looks like I need to speed up a little bit here. Okay, so physical space threats. Okay, you can call it space debris. So, but not everything that's a threat is debris. We worry about operational satellites as well. In terms of space debris, we've got orbital debris, which is entirely man-made stuff. It's in Earth orbit, so it has to follow the physics of Earth orbit. Meteoroids is all natural stuff, and that's coming in from whatever direction, and that the direction that is coming from and the direction the spacecraft is going at the time determine how fast it's going to hit. Like I said, we worry about the non-debris objects, even more so now with SpaceX putting up the Starlink constellation. I think I saw the other day they're up to 2,600 spacecraft in just that constellation. We didn't used to have 2,600 in operational spacecraft in all of Earth orbit. So that's more than doubled the threat. And those are mostly clustered pretty densely at right around 550 kilometers. So if we operate below that, like space station, that's not as big a threat. If we operate above it, we've got to get through that constellation to get there. So the debris environment, most of what I work on is low Earth orbit. Okay, as you expand further out from Earth, the volume gets larger and larger. So the density of all that debris gets lower and lower, and there's, I think, 1/10 or even less than that debris at geo versus low geosynchronous orbit versus low Earth orbit. Where does it all come from? A lot of it is rocket bodies. The upper stages often do not come back down for months or years. Some of it's dead satellites. Some of them I helped decommission. Some of them are explosions. I worked on one not long ago where a spacecraft that we had passivated exploded years later, and it was a real head scratcher to try to figure out how. Another is collisions. Some collisions, most collisions you would hope are unintentional. Lately, we've had a couple of anti-satellite tests, which is an intentional collision. So orbital debris, like I said before, it's in orbit, so it follows orbital physics. Okay, if your satellite is headed this way and your debris is headed this way, their impact speed in the front can be as much as 14 kilometers per second. it took me years just to get my head around that what that number is. It's just extremely fast. But if your satellite is headed this way and you hit the side of it, you're hitting at about 7 kilometers per second, which is still a huge number, but it's a lot less, but it's smaller. If you come up from behind, you have almost no impact velocity and a much lower impact energy. So the risk to that spacecraft varies by what direction it's traveling, and also the direction of the projectiles that might be hitting it. Okay, so usually most of the debris is traveling in a near circular orbit. And so it might hit from the side or the front, but almost very rarely the zenith, which is facing out into space, or nadir, which is facing the Earth. I'll show you the size distribution in just a moment. Most of my, I say my, most of our robotic missions are shielded to about 1 to 2 millimeter penetration. Space station is shielded to about 1 centimeter, and you'll see in a moment what that means for us. So this is for a typical Earth orbiting, Earth observing space telescope. This is, I believe, the Aqua, or in Aqua or Terra. They're all at that same altitude. So you can see the blue line here, which is what is trackable. Now we've recently dropped that blue line. It used to be at 10 centimeters. Now we're down to about 4 centimeters with the new space fence radar. But it's still, there's this huge red oval of non-trackable but lethal debris, things that can penetrate Aqua, but I can't see them. There's no way to get out of their way. So there's 10,000 times more objects that we can't see and can't predict versus the ones that we can see and get out of the way. In fact, they did that just the other day. Where is the debris? This shows the evolution over the course of 20 years. The purple line down there at the bottom, that's 2020. By the black line, 2010, you can see there's a lot more debris, a lot more tracked objects, especially in the 800 to 850 kilometer region. By October 2020, there's fewer at 800 because a lot of those have dragged down and they're at 700 or 650. And you can see those peaks are shifting down as well. There are also some new peaks at 550 because of all of those Starlink spacecraft that I talked about before. This is how debris has grown over the years. You can see all the way back to 56 that we had basically no debris. Okay, and then as the years progressed, the blue line active spacecraft has really swung up lately with the Starlink constellation. But that purple line is the one that really bothers us because that's collisions, both intentional and unintentional collisions. It's also explosions. Anytime something that's in orbit breaks up, it shows up on that purple line. So you can see a big jump for the Chinese ASAT test in 2008 or 7, and another one big jump for the Iridium Cosmos collision That's kind of settled out a little bit, but then we've gotten some more that have picked up lately. And some more that I think would not be on this because this plot only goes out through February of 21. Meteoroids, I said before, these are natural debris, so they're coming from whatever direction the source was. Okay, they don't follow orbital physics, Earth orbit physics. They're more following the somewhat heliophysics and maybe even the physics of the galaxy. Okay, it becomes important even which side of the Earth you're on when that meteoroid hits, because the Earth itself is rotating on the order of, I think it's 20 kilometers per second. So you adding speed on one side, on the other side, your spacecraft would be moving away, and you've got much lower speed if the meteoroid hits you on that side. So usually we consider meteoroids to be in the range of 30 to 70 kilometers per second. Well, if it took me years to get my head around 14 kilometers per second, it took a few more years to get my head around what is 30 kilometers per second mean? That's just unbelievably fast. What it means is that teeny, tiny little meteoroids, a tenth of a millimeter, can penetrate right through your spacecraft if you're not careful. Remember that impact energy is 1/2 mv squared. So when V gets up to 30 to 70 kilometers per second, V squared gets to be enormous, even if the mass is very low. So this is the size distribution. This is actually put across 18 orders of magnitude of mass. So this is quite the stuff down on the left side is really, really, really tiny dust, even smaller than dust. The blue line is about 1 microgram. And so that's about a tenth of a millimeter in diameter. And those are the ones that's about the penetration limit that we're looking at for meteoroids. So how do we mitigate against all of that debris? The big thing is shielding. We like to build shields when we need them. A lot of spacecraft can accept the kind of risks that we're talking about. One thing you can do is put all of your sensitive components, and by sensitive components, I mean the things that operate the spacecraft itself. The instruments usually need to be on the outside, but you can put all of the rest of it inside. Well, then the spacecraft wall helps with shielding. But when we need additional shields, what we do is we put a ceramic layer on the outside, and then it leaves some sort of a gap. Maybe we have to fill it with foam just because constructing a large shield requires some support. Otherwise, the layers come in and touch. But we leave some gap, and then we can bring in Kevlar, which is a very tough material, but doesn't serve to break up the projectile the way that a ceramic layer does. So you get beta cloth or Nextel as that first layer, then an open gap or maybe some foam, possibly more layers of Nextel. We're doing that right now on a Mars mission. And then we put in Kevlar to grab the broken up debris, the broken up shrapnel, and prevent that from either hitting the component or at least slow it down dramatically. It's very difficult to shield against meteoroids. Like I said, that Mars mission, we're having to put in, I think it's 4 ceramic layers to break up these meteoroids enough and slow them down enough that the Kevlar can stop them from doing further damage. So in addition to shielding, another thing we can do is redundancy. If you absolutely need your S-band transmitter in order to perform the mission, put in 2 of them. Now that has a penalty. Sure, 2 boxes cost more, they weigh more. You've got to have some sort of switching between them so that if one dies, you can switch over to the other. So you've got to have extra complexity there, but it gives you a much greater lifespan for your spacecraft if you can put in that redundancy. Another thing is we fail safely. Again, the safe hold mode, where the spacecraft is constantly checking on itself and say, hey, did something go wrong? And okay, I'm going to hunker down until the ground tells me what to do next. Okay, I'm not going to go into detail on this in the interest of time, but what we do is we take that curve and we say, okay, my tolerable risk level means that I can have 1/100th of a strike per square meter per year on this particular spacecraft, this as the example, and that's the green line. We'd bring that over to the environment model, and it says, okay, well, that lines up to a 2 millimeter projectile. So you need to protect your box against all of the critical boxes against 2 millimeter or smaller. Anything larger than 2 millimeters is probably going to get in, but fortunately you can see this curve dropping off. There aren't going to be that many of them. So that's how we go about picking how big the shield needs to be. Because if you want to launch with 0 risk, I can tell you right now, it's going to cost too much for anybody to afford. It'll weigh too much to ever get off the ground. It'll take so long to build it that it'll be obsolete before you launch it. So there's never going to be a mission that has 0 risk. There's always going to be some risk you have to accept. And this is how we go about it. Okay, other things that we can do to mitigate risks. We prevent debris, and that's 90% of Yvonne's and my job. We look at the spacecraft all the way back at the proposal stage, and we start saying, okay, you need to pay attention to this component. You need to pay attention. Okay, you're going to have problems with the population of debris because you're going into a very dense orbit. You may want to consider a different place. At the end of the mission, you can't just walk away from a spacecraft. Okay, you've got battery. The solar arrays are still going to be charging those batteries. Well, a lot of these batteries need to be watched on a daily basis to make sure that things aren't getting out of control, and maybe we tweak charge rates and things like that. Well, if the mission's over, nobody's watching, and you can walk away from it, and the solar arrays keeps charging the battery starts going out of control, nobody's watching, and the battery can explode. We've seen it happen mostly on Russian missions. So what we want to do at the end of the mission is we deplete all of that energy. Ideally, We drain the battery and then disconnect it from the circuit. A lot of people don't want to do that because that means a single point of failure for the mission. If that happens early, the whole thing dies and there's no way you can recover it because you've disconnected all of your power and drained everything down. So we have to be careful about how we do the decommissioning plans, and that's my big thing, is try to invent an off switch that nobody built in the first place. Same thing with propulsion. We're leaving hundreds of pounds per square inch of pressure inside propulsion tanks, and sometimes 10, 15, 20 kilograms of fuel. Well, that's not good. If you get a particle, a meteoroid or an orbital debris piece that comes through and tears that tank open and ignites the propellant, the whole thing blows up, and now your one spacecraft just became 2,000 pieces. Another thing we do is we look at the disposal. All the way back at the proposal phase, Yvonne is talking with folks and saying, okay, how are you going to get rid of this at the end of your mission? Scientist is saying, hey, I haven't even built it yet. We got to start thinking about it early. International standards are that you get about 20, you can have up to 25 years after the mission while the spacecraft is decaying out of orbit. If it's going to take longer than that, you need to push the spacecraft down or don't launch it to as high an altitude. If you're in geosynchronous, we have a super geo graveyard orbit that everybody pushes up and then passivates up there. We also track everything from about the size of a golf ball up, and we can issue warnings and say, okay, Aqua, there's this softball size thing coming at you. It's going to get as close as possible on when Thursday afternoon. It's going to come within a kilometer of you. And we're going to keep watching it, and maybe we get better tracking data and it passes by harmlessly, or maybe Aqua says, you know what, I'm too nervous, I'm going to move a little bit. And so they slow down some, the debris passes, and then Aqua comes through, increases that distance between them. So we do have some options. It's all assessing and managing risks. So that was my last slide. Probably left you with some questions, so fire away.
I'm sure a lot of us have questions. I have put some on the chat board. Please make sure you either write on the chat board and Robert can read them, or I or Ken, somebody can read them, or directly you can ask.
Okay. Yeah, I don't see anything in the chat right now.
We have a separate SOAP chat.
Yeah.
Ravi, you had some questions?
Yes, I have a lot of questions, but I want to give benefit of doubt to others. But if you want me, just the top level is, remember during Apollo, we had a meteorite size curve developed by my colleague, Julius Dohnani. I wonder if it is still surviving in the scientists area. It's called Dohnani curve. It was a Hungarian scientist who was working with me during Apollo.
Yeah, one of the things that came out of Apollo was the whole meteoroid environment office at Marshall.
Yeah.
We work very closely with Bill Cook and Althea Moorhead down there. Um, they maintain and update models, not only in Earth orbit, but reaching out. They're helping us out with the Mars orbits. Okay, sorry, I had a pop up on my screen here. Um, they're working all of those environment models. Um, so they're looking at the comets and the other sources for interplanetary meteoroids. Yvonne just did some work with the Lucy mission going out to the Jupiter Trojans. And so it's still a very active field. Uh, like I said, those things they tend to be smaller, but much faster. So they're hard to shield against, and hopefully we're able to build the spacecraft in a way that it can survive.
I have a question from Mike Bennett.
Janet and Mike.
Mike was first. Mike?
Oh, okay. Yeah, so I don't know if you looked at the ontology side of things. One of the common abstractions we use in risk modeling is risk equals probability times impact, which is a very core ontology of risk that can be applied in any domain, like finance, for example, where impact would be loss given default or something. Some of the slides you show are a much more literal probability times impact. So I just wonder, have you sort of used common models for risks? Have you looked at ontology modeling for that at all, and how does that work?
Yeah, well, Yvonne and I tend to use the word consequence instead of impact, because when you're in orbital debris, impact has a different meaning.
Indeed.
But yeah, I thought about putting it. I mean, there were 20 more things I could have put into the slides, but I needed to leave some time for questions. Yeah, we normally use a 5x5 matrix, and we've color coded green, yellow, and red for those risks. And your acceptable risk level are mostly the ones that show up in the green. Low consequence or low probability of occurring, low likelihood of occurring. The more likely the risk gets to be, and the higher the consequence, then you're pushing up to that upper right corner, where you start really worrying about, okay, how do we mitigate those risks? And like I said, we've got a whole division, the Office of Safety and Mission Assurance, that's all they do, is look at, assess, and then manage those risks along with the project. Did that answer the question?
Yeah, thanks. That's cool. Cheers.
Janet?
Thanks. Very interesting. My husband, Michael, who is also here but muted, worked at JPL and then at NASA Ames on space debris, briefly at Ames on game modeling of looking for trade-offs among countries, parallel to the what was the original Kyoto Protocol. But anyway, my question is more on the ontological side. Or I'm sorry, this is more of a comment, but the whole field here is interesting from an ontological perspective, ontological modeling perspective, because what happens in space is relatively constrained. So you only need to consider a few factors in your risk assessment in space, as opposed to what happens on Earth. now there are consequences for what happens on Earth. So you sort of have a two-tiered modeling problem of a nice clean arena in space, and then consequential effects on Earth. And do you model both of those? I know you model, in great depth what happens in space, but do you also model the, political, economic, other consequences on Earth of particular events in space?
To some extent. I will amend. I will amend something that you said, that we have fewer threats in space. I think we have different threats in space, but we certainly have quite a few, and a lot that I didn't touch on. And a lot of times there are Earth analogies. Okay. We had a strong weather front that came through here 2 days ago. Okay. Well, in space right now, the sun is going through a phenomenally active period where we're seeing enormous sunspots that are throwing big flares. Okay. That's not part of our normal baseline radiation level, but every time it's throwing a big flare our way, we get more radiation. So there's a lot of other things besides the few that I could touch on in this talk. But yes, what I think you were asking is, do we worry about, for example, the operations center flooding? And yes, we do. We have a group at Goddard, a Space Asset Protection Group, who look at political situations. They look at weather. And they can, if the project requests it, they can go in and assess whatever it is, from the launch site to the operations center. Certainly space station is very sensitive to political concerns. So far, we're able to operate space station with very few impacts, but there is some amount of consequence of the tensions between the U.S. and Russia right now. So I hope that answered your question. If not, feel free to
Yes,
rephrase
I think, yeah, I didn't mean that there were, even with what you're identifying there, with the sun and the radiation consequences, it still is a cleaner environment than trying to model anything on Earth where you don't have a big delay for somebody to come in and mess things up, to get there physically, where you'd be able to see
Right.
that someone is trying to do something.
Yeah.
So
Most
it's a
of
cleaner,
our
right?
most of our threats are more predictable, but not all of them.
Right. Yeah, interesting. So what are the unpredictable effects? What are the unknowns? List the unknowns for us.
One quick
Well,
question.
coming from the parts world,
Uh-huh.
we had parts failing for new mechanisms we had never seen before. We were making a DC to DC converter in a larger can. It was a big hybrid with a hermetically sealed lid. And those things, they worked great in all military applications. And we said, we want to fly this in space. And we start testing it, and we found that the lid, when you put this thing in a vacuum, the lid was flexing.
Mm.
And it was actually pulling the transformer apart.
Mhm.
Unfortunately, that happened on orbit before we learned about it on the ground. So there are things like that that we can't predict. They're great learning opportunities for the next time, but we can still lose missions because of things like that that we just had no way of expecting.
Interesting. Let someone else ask questions. Thanks.
Is there anyone else? I have a kind of question about, I mean, are you considering techniques for deorbiting debris? Is that part of this, part of your, part of the tasks that NASA is looking at? I mean, there are things like laser brooms and stuff that I've seen.
It's a great question. And the agency, we do discuss it. Unfortunately, I mean, I've looked at about 36 different proposals for ways to remove small particles, medium, large spacecraft. If in the cases where we can identify an effective method, it is still so very expensive and no one's paying for it. And so what we really need to find is a way to make it economically feasible to do to more than remove one object. Yes, it's certainly something we look at. We are already past the tipping point. All of our models say that if we stop launching tomorrow, the fragmentation debris is going to continue increasing for the next 200 years. And the only way to prevent that is to remove at least 5 large objects, rocket bodies, large spacecraft from orbit per year for the next couple decades. Nobody's got the money to do that. Oh, if you want to do it, I mean, I was talking with Goddard's chief engineer yesterday at lunch about how to do it. Oh yeah, I would make a stack of 5 bagels and I would bring the spacecraft down into the first one and, then separate from it, and a week later to do a deorbit burn, and we go through this stack of 5 and then send me another stack of 5, and I'll keep doing it. I know how to do it, but are you going to give me what, 10 million a piece, 20 million a piece, 50 million a piece, 1 million a piece? Nobody's got that money to start clearing out that debris, and nobody's got a more effective method than about, I'll say 10 million per object to remove them, and the money's just not there. If you've got a good idea, I'd love to hear it.
Oh, no, I was just asking you
Yeah.
if you have the concepts kind of in a way that you can do a kind of analysis, so you can balance the risk that you're facing with the costs to mitigate those risks.
Yeah.
So it's similar to the techniques you've been talking about all along.
Sure.
The consequence times probability, look at the costs involved.
Laser removal was a big thing, 6, 8, 10 years ago. But you've got to be able to find the debris very, very accurately before you can hit it with that laser in order to ablate one side and move it down out of orbit. We were working with Ames to do that. We couldn't get the funding for the laser orbital debris laser ranging, and we're still trying to get that. It's difficult. It's complex stuff. Yes, you can remove things by hitting one side with a laser, but you got to be able to find it and hit the right thing with the laser while you're not hitting something else or, God forbid, an airplane. I wanted to point out that my email address is on the slide there, and I guess it was the slides are distributed. So if anybody comes up with questions later, feel free to email me.
Okay. Robbie, do you have any other closing comments?
Well, Robert, do you have any? I'm very happy to have heard this. I have a lot of questions like smart materials, self healing smart materials to repair damages that can be repaired. Then I also have questions on how likely is some segment of commerce likely to evolve that will deorbit the satellites, especially the lower ones around 700 and 550 that are going to crowd our space internet and space like that. So yes, some effort is required.
Are you talking about the Starlink constellation and some of the others?
Yeah, things of that sort are going to crowd further.
Okay.
But they have
I
also
know that.
relatively shorter decay times compared to geostationary. So maybe they
Yes.
can deorbit with built-in capabilities, things like that.
Well, that's where there's an internationally agreed 25-year rule, and NASA has codified that. It's an absolute requirement for all of our missions. If you're in low Earth orbit, you've got to be out of orbit within 25 years after the end of the mission. So to take, let's say Aqua, for example, I know that their plans, and they've already started this, they've stopped maintaining their orbit. They're starting to drift down slowly while they can still collect science. And when they get down to the point where they can no longer collect science, they're going to take all of the residual fuel that they have and lower the orbit even further. And from that lower orbit, they'll be within about 20 to 25 years. And a lot of that depends on the solar activity. If the sun stays as active as it is, it's going to drop faster, and it's also going to drop faster after they lower the orbit. SpaceX has similar plans for Starlink. They're using electric propulsion, so they tend to come down a lot more circular. The orbit just kind of spirals down. They're claiming, I think, as little as, depending on the solar flux conditions, less than 5 years and possibly much less than 5. So there are good plans for the spacecraft that are active. And by the way, Aqua did not have that requirement when they launched. Aqua has been up there for almost 20 years.
Yes.
And it's now a requirement, and they've altered their operations to meet the requirement.
I showed the last month's Aqua picture of Saharan desert storm, dust storm. But you are right, they have stopped maintaining the corrections for geometry and all this. And that's very good byproduct. Thank you. Well, I am done for now. I will email more questions and we'll have the chat captured on the board.
So with that, I will adjourn the meeting, stop the recording.
And we